distance and accumulated change. In physics, the way that we compute distance is by multiplying velocity times time. This equation represents a way that we can use a rate and a time to determine information about the original function position. Think about the relationship between position and velocity. Velocity is the derivative of position. Now, distance is going to be the change in position. So we're able to use the derivative of position in conjunction with our independent variable time to learn something about the original function, which is position. If we were to take this formula and make it a little more broader, we could write this as rate times time. So here, instead of velocity, we have rate, and time we still leave as a factor here. Now, what does that tell us? That tells us if we have the derivative of a function and we know how long we are at that particular derivative, that will tell us something about how the original function changes. Now, what does this mean in the bigger context of the course? Well, so far, we've been focusing on understanding the derivative, deriving the derivative, using formulas to find the derivative, and applying the derivative to find things like local maximums, local minimums, etc. Now, this chapter asks the question, if we have the derivative, or if we start with the derivative, what kind of information will that tell us about the original function? And so this is where we begin. Now, keep in mind, if we want to multiply a rate times time, we need to be very conscientious that our units all match up. So we'll keep an eye out for that as we go. So let's start with an example. If you were to travel going 50 miles per hour for 3 hours, how far did you travel? Now, you may have automatically thought 120 miles, but let's see how we get there. So if we're going 40 miles an hour, we're going to write the units here. We can multiply that by 3 hours because that's how long we are going at this rate. So we have a rate times time. And that's going to tell me what? Well, here the hours are going to cancel. And 40 times 3 is 120 miles. So if I multiply these two numbers, I get 120 miles. What does that really mean? That means that my position changed by 120 miles because I went at that rate for 3 hours in time. So we go back to our original equation, rate times time. That 40 miles per hour is a velocity. Remember, velocity is the derivative of position. And our answer, 120 miles, tells us how much our position changed. Now, multiplying that may seem natural, and you may have been inclined to do that. There's another way that we could have solved this problem. What we can do is we can graph our rate versus time. And let's see how that works and what that will tell us. So here, we want to graph our rate versus time. So here we're graphing the derivative. And so my rate here is constant, right? It's just 40. It's not 40t or 40t cubed or anything like that. So if your rate is just a number, that just means that you have a horizontal line at that number. So here, I have 40, and I'm going at 40 from time equals 0 to time equals 3. So my picture looks like this. I'm going 40 miles an hour for 3 hours. So my rate, again, is in miles per hour, and my time was in hours. So here, when we graph the derivative, what we can do is we can find what's called the area under the curve. So what we're looking for here is that we want the area between our function and the independent axis here. So that area, you can see, is the area of a rectangle. So we're going to be doing width times height. So again, we'll do 3 times 40, and we find that that area is 120. That's the same thing that we got up here. Okay? So what that tells me is that I can use a graph now and look at areas to tell me the same thing I can get using algebra. Now, this may not seem like a thing that we would logically want to do at this point, but as we move along, we'll see why this graphical representation is going to become very important to us. Let's look at another example. Example 1. If you were to travel 20 miles per hour for 3 hours, and then 50 miles per hour for 4 hours, how far did you travel? Compute this algebraically and graphically. So this is similar to the problem we just looked at, only now, instead of one constant rate, it seems like there's 2 legs to our trip, or at least a change in our velocity. So for the first part of our trip, we went 20 miles per hour times 3 hours. Again, we need to make sure our units match up. The hours are going to cancel, and I get 60 miles. So for this first part of the trip, I know that I went 60 miles. Now for the second part of my trip, I was going 50 miles an hour for 4 hours. So again, the hours are going to cancel, and I get 200 miles. Now, if I add up the 2 legs of my trip, I get that I traveled 260 miles. So if I were to graph this scenario and analyze it graphically, again, I'm going to plot my rate on my dependent axis and my time on the independent axis. So my rate here again is going to be in miles per hour, and my time is going to be in hours. And so the first rate that I'm traveling is again constant. That 20 miles per hour is just a 20. There's no variable with it, which means I'm going to have a horizontal line, and I do that for 3 hours. So I'm going to do that from time equals 0 to time equals 3. Looks like this. But then I go up to 50 miles an hour. So I'm going to put 50 up here. And I'm at 50 miles an hour for 4 hours. So I'm going to go from 3 to 7 because that represents a 4-hour chunk, right? And since there's a sequence here, I graph my 20 mile an hour rate first and then my 50 miles per hour rate. Again, I want to get the areas under the curve. So this first rectangle, my width is 3 units and my height is 20. So that gives me an area of 60, which represents the 60 that I got over here algebraically. And then from time 3 to 7, the width is 4 units and the height is 50 units, which gives me 200, which is the same thing I got algebraically over here. And adding up these areas, again, I get 260 miles. So again, I'm able to graphically and algebraically solve by using my derivative, which here is a velocity, in order to find out the information I need. Let's look at one that doesn't involve a velocity, but does involve a rate, just so we can see how else this will present itself. Example 2. Suppose a population is growing at a rate of 2,000 people per year for 3 years, and then 3,000 people per year for 4 years. What is the total change in population over these 7 years? So again, I can look at each part of this population growth individually. So first I had 2,000 people per year, and that was for 3 years. So again, my units, they match up and they cancel here, and I get 6,000 people. And then for the second part of my population growth, I have 3,000 people per year. And that time, it's for 4 years. So again, the years units are going to cancel. 3,000 times 4 is going to give me 12,000. So I had 6,000 in my first years of growth and then 12,000 in my second years of growth. Adding those together, I get 18,000 people. Similarly, if I wanted to graph this, again, I'm going to graph my rate versus my time. My rate, again, is in people per year, and my time is in years, so those match. We always need the independent units to match the bottom of our rate in order to be able to do this kind of analysis. So 2,000 people per year, again, that's a constant rate. So our constant rate is going to happen for 3 years. So 2,000 people per year for 3 years, and then 3,000 people per year. So our rate's going to jump up to 3,000 for another 4 years. So that goes till 7, from 3 to 7. And now I can find my areas, which again will be 6,000 and 12,000. And I can add those areas together. And again, I get 18,000 people. Now, I need to be a little bit careful about what this means. This does not mean that my population is 18,000. It means that my population changed by 18,000 over those 7 years. And because it's a positive number, my population grew by 18,000 people. I don't know what the actual population is because I don't know how much it was to start. All I know is how much it changed over the 7 years. So it grew by 18,000 people. Now, let's see why this graphical representation becomes really important to us in the next example. Example 3. Suppose the rate at which a skateboard is moving over a 60-second interval can be written as f of t equals 3t, with f of t in feet per second and time t in seconds. What is the total distance traveled by this skateboard over the first 10 seconds? So here we have a rate, which is 3t, and we have a time, which is 10 seconds. Only now our rate is not constant. So here we now see that there's a variable in our rate, and we have to figure out what we can do with that. We run into a little bit of trouble if we try to do rate times time, like we did before, because 3t times 10 gives us another function, right? Not a numerical answer. So that means that we can't depend on that equation anymore. So instead, we're going to go to our other approach, which was to graph our function and look at the area under the curve. So 3t is a linear function. So remember, we're doing rate versus time. My rate here is in feet per second, and my time is in seconds. So again, my units match. If they didn't, I would have to convert them to match. If for some reason I had time in hours, I would need to convert that to seconds so I could draw my picture. So 3t is a linear function that's increasing. Looks like that. And time, we said we want to know what's happening during the first 10 seconds, which means I'm looking for the area of a triangle. So the area of a triangle is 1/2 base times height. So if I know base and height, then I can use this method to find out my total distance traveled. So my base here is 10, right? That's my time unit, and I already know that I'm looking for 10 seconds. So I do know that part. The height, however, is a little more complicated. So my height here is dictated by the function 3t. My height would be the corresponding y value for this function for any given t value, which means that if I take t equals 10 and plug it into my function, that will give me the corresponding height or y value at this point. So if I plug a 10 into 3t, I get 30. So that means this has to be 30. Now, before we crunch this number, let's take a look at the units. So 10 is 10 seconds, and 30 is 30 feet per second. This is important because here we see that the seconds cancel, and now I have half times 10 times 30, which gives me 150 feet. So the question is, what is the total distance traveled? And the answer is 150 feet. So again, we have to be careful with a couple things. First is we have to know what information is important from the problem. We know that we were moving over a 60-second interval, but we never used the number 60. That was somewhat irrelevant to what we were looking at, other than we knew that our time had to be somewhere between 0 and 60. Next, we needed to know what was our rate. So the rate was the 3t. That's that part we had to graph because we didn't have a way to multiply it algebraically, and then our independent values had to do with the time, so that 10 seconds. Putting that all together graphically, we were able to compute the area under the function. So far we've used area under the function to look at areas of rectangles and areas of triangles. As you can imagine, our goal is going to be to try to find areas under functions that are not linear, right? So things that are curved, that are wavy. How are we going to go about finding those sorts of areas? So this lays the foundation for being able to do that. So let's look at an example that's not linear, and we can start to motivate how we're going to approach these nonlinear functions. Using a table to estimate a function. Suppose we measure the velocity, v of t, in feet per second, of a bicyclist racing down a flat road every 2 seconds. How can we best estimate the total distance traveled over the 10-second interval? And how do we graph this scenario? So first we're going to talk about how we estimate it. Then we'll take a look at the picture of what we did. So we have to be careful here. Remember, if our rate was constant, we could do rate times time. However, you can see that our rates here are changing. The velocity is 0, 5, 7, 10, 15, 22. So it's not the same at every point. And we also don't know what the actual function is for velocity. So we can't even try to see if it's a rectangle or a triangle like we did before. So we need to come up with something better. The other thing we have to be careful about is what our time units actually are. So what we don't want to do is we don't want to do something like time equals 0 times rate equals 0 and time equals 2 times rate equals 5. Because if you multiply something like 10 times 22, that would mean that you were going 22 feet per second for the entire 10 seconds, which simply is not true. So what I want you to notice here on my table is that my time units are equally spaced. Between every two numbers is 2 seconds, so we're counting by twos, which means that we can break this down into small 2-second intervals. So we're going to consider what happens between time equals 0 and time equals 2. That's our first little interval here. And then we're going to look at what happens between time equals 2 and time equals 4. That's our second interval here. Then we'll look at what happens between time equals 4 and time equals 6. And then time equals 6 and time equals 8. And then finally, what's happening between time equals 8 and time equals 10. So this is what we're going to do. Because if we look at what's happening in each of these little intervals, if we can figure that out, then we can just add up all the things we figured out. Just like when we had 2 legs to our trip or 2 parts to the population growth, we were able to figure out each piece separately and just add together our answers. So that's what we're aiming for here. So I want you to notice that for each of these little intervals, they're each 2 seconds long. Okay? So that means that my time for every single interval is 2 seconds. That's really important. Now remember, if our rate was constant, we could do rate times time. Now we said that the rate was not constant. However, what we can do is we can take each 2-second interval and we can fix the rate just for that 2 seconds. But we have to do it in a way that's methodical. So what that means is if I'm considering what's happening between time equals 0 and time equals 2, my first 2-second rate, I'm going to assume that my rate was constant, and I'm going to pick that rate to be the one on the left. So there's 2 rates here. There's 0 and there's 5. I'm picking 0, the one on the left. So now when I do rate times time, I'm going to do 0 times 2. And again, that's 0 feet per second times 2 seconds. From time equals 2 to time equals 4, again, I'm going to pick the rate on the left. So rate times time is 5 times 2. Time equals 4 to time equals 6. I'm going to pick the rate on the left. Time equals 6 to time equals 8. Again, pick the rate on the left. And time equals 8 to time equals 10. Again, pick the rate on the left. So again, what I'm doing is I'm assuming that the rate is constant for each 2-second interval so that I can use the formula rate times time. Now, as I said before, each interval is only 2 seconds long, and then the rate changes, just like it did when we were doing the trip with multi-parts. But that's okay, because if we add up all these little pieces, it should give us the total distance traveled. So what we want to do is we want to add what's going on here. So if we crunch all those numbers together carefully, we're going to get 74 feet. Remember, we're doing feet per second times seconds. So when we add these all up, we get 74 feet. Now we were very methodical. We always picked the rate on the left, and then we went through our entire table to represent each time interval. However, if you are this bicyclist and you are indeed racing, right? So you want to cover as much distance as you can, you're probably going to be really angry with what we did because we didn't ever even use the 22, which was your fastest rate in all of the measurements. So it turns out that what we did is called a left-hand estimate. So 74 is a left-hand estimate. Now, you can imagine why it's called that, right? Because we always pick the rate on the left of the two rates. So there was no reason whatsoever that we couldn't have done the same thing, but used the right-hand rate for each estimate. So let's go ahead and see what happens if we do that. So from time equals 0 to time equals 2, instead of picking the rate on the left, which was 0, I'm going to pick the rate on the right, which is 5. So now I'm going to do 5 times 2. My rate was 5. My time was 2 seconds because time equals 0 to time equals 2. Plus, now from 2 to 4, I picked the rate on the right, which is 7. So 7 times 2. Plus, from 4 to 6, if I pick the rate on the right, that's 10 times 2. Plus now from 6 to 8, the rate on the right is 15 times 2. Plus, now from 8 to 10, I have 22 times 2. So I multiply all these smaller pieces together, and I add them up, and I'm going to get, 118 feet. Okay? And this is called the right-hand estimate. And it's called the right-hand estimate because, again, we're always picking the rate on the right. So what does that mean? What does that tell us? What do we do with this information? So this is going to give us bounds, okay? What this means is that our total distance traveled, we'll call that TDT, total distance traveled, has to be between 74 and 118. It can't be anywhere else. Given these rates, it has to be between these two numbers, right? And these, again, are in feet. So that's useful in some ways, but these numbers are kind of far apart. If we didn't have any more information, there's also something called the best estimate. And the best estimate is the estimate that you get when you average these two things together. So remember, when you average two numbers together, you add them up and divide by 2. So when we do that, we're going to get 96 feet. Now, does that mean that I traveled exactly 96 feet? No. No, what it means is that's my best guess based on the information that I have. If I had more information, I'd be able to refine my guess to make it better. But what's really important here is this idea that we are fixing the rate to be constant for these time intervals, okay? And there's some other terminology that comes along here that's going to be really important. So I'm going to present it now in the context of this problem, and we'll define it more thoroughly later. So the first thing is delta t. So in this problem, my delta t is 2. Okay, your delta t, or sometimes delta x if you're using the variable x, is going to be the interval size that you're using or what you're counting by in terms of the independent variable. So delta t here is 2 because I'm counting by 2's, 0, 2, 4, 6, 8, 10. The other important variable here that we're going to start talking about is n. N is the number of estimates that I'm making. So here I had 1, 2, 3, 4, 5. So here my n equals 5 because I used 5 distinct time intervals to approximate what was happening. Now, you may not have put this all together yet, but we're going to see each of these time intervals represents a rectangle. So when we graph this to look at this situation, we'll be able to see that we used 5 rectangles to approximate the area under the quote unquote curve to approximate the total distance traveled. So let's look at a picture of this and see if we can visualize what's going on in this scenario. So our picture here is a graph of your velocity versus your time. So remember, all of our times were in 2-second intervals. So you can see here that we're determining what's happening between 0 and 2, 2 and 4, 4 and 6, 6 and 8, and 8 and 10. When we do a left-hand estimate, for the first 2 seconds, we assumed that the rate was 0 because that was the rate on the left. So if you look at what's happening in the orange, you can see that we have a line at velocity equals 0 from 0 to 2. And then from 2 to 4, the rate we assumed was 5, so we have this constant line at 5. From 4 to 6, we assumed the rate was 7. That's a 7 there. That one we said was a 5. We assumed this rate was 10. And we assumed this rate was 15. So you can see that we're constant for each 2-second interval. And then in order to get the area of each block, we are doing our rate, which is the height of the block, times our time, which is 2 seconds for each, or the width of the block. So if we do 2, which is the width, times 15, which is the height, right? That's our y value. We get 30. We have 2 times 10, which is 20. 2 times 7, which is 14. And 2 times 5, which was 10. We'd also have 2 times 0, but that's 0. And it was adding those numbers together that gave us the 74. So this is, again, a left-hand estimate. That's what we're doing. We're turning each time interval into a rectangle. So we do the same thing with the right-hand estimate, right? So now, for each interval, we're assuming the rate on the right. So that's 5. And then this one goes up to 7. And then this one goes up to 10. This one to 15. And this one to 22. So the area of this whole block is 22 times 2, because again, the width is 2. That's 44. This is 15 times 2, which is 30. Again, this whole block, it crosses over. 10 times 2, which is 20. All right, this one's 14. This one is 10. So we can see that these areas are represented the same way we were graphing them before. Only now we're turning each of our little intervals into these constant rates so that we can use rectangles, because rectangles are something we know how to get the area of. Now, something even more interesting happens when we're graphing a scenario like this. If we connect the points of the left-hand approximations, right, we get something that looks like this, which is the same thing we get if we connect the corners of the right-hand approximations. So what I want you to notice here is that my orange rectangles, right, if we're approximating the area under the curve, the left-hand estimate is an underestimate, right, because it doesn't quite capture all of the areas. It's missing all of these areas under the curve if we were trying to get the exact estimate. The right-hand estimate in this scenario is an overestimate, because look at all the extra area above the curve over what the actual area is, right? So When we find a left and a right hand estimate, one of them is an overestimate and one of them is the underestimate. The overestimate is going to be whatever the bigger number is, and the underestimate will be whatever the smaller number is. So that's why we have that interval of 74 to 118. One of them is too much area, the 118, and one of them was not enough area, which was the 74. It has to be somewhere in between. But we get a general sense of what our graph looks like by connecting those points from the left and the right hand estimates. And again, with the left hand estimates, the red rectangles, you can see that the left hand corner of every rectangle touches our function. With a right hand approximation, it's the right hand corner that always touches our function. So we can predict that our function looks roughly like this because we're able to connect those corners. So let's circle back to the different terms we've learned in the vocabulary we've been using to talk about these estimates. So the left hand estimate, we assume that the rate on the left is the constant rate for the small time interval. A right-hand estimate, we assume that the rate on the right is the constant rate for each small time interval. The overestimate is going to be the larger number from your left and your right-hand estimates. Your underestimate is going to be the smaller number from your left and right-hand estimates. It's not always the same. So whenever you're talking about over and under estimates, you have to compute both the left and the right and then compare the numbers you get. For our variables, we had delta t. So delta t was these small time intervals we were looking at of measurement. In the last example, delta t equaled 2 because we were counting by 2's. N was the number of rectangles that we're using to estimate a function. And now we're going to add on a and b. So a and b are going to be the starting and ending point of a function defined by its independent values. So where are we looking between what two values? That's your a and your b. We'll see why those are relevant in a minute. So if we want to make our estimate better, right, so that we don't have as much over or under, how do we do that? So let's look at another example. Suppose that during this bicyclist racing down the flat road, we had the ability to measure the velocity every 1 second instead of every 2 seconds. How does that change our estimate? Is it better or worse? So let's take a look at this table and let's talk about some of our new variables. Let's start with delta t. So remember last time delta t was 2 because we were counting by 2 seconds. Here, my delta t equals 1 because now I'm counting by ones. I was able to measure every 1 second. My a is going to be my starting point, so that's 0. My b is going to be my ending point, which is 10. And then my n, which is the number of intervals that I'm going to be using, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can count them by looking between how many points I'm going to be using. But I also have this relationship that b minus a divided by delta t equals n. Similarly, I can use that b minus a divided by n equals delta t. So if you know the length of your interval, so here b minus a is 10 units long, so b minus a is 10, and you know either your delta t or your n, you can use that to find the other one if you need it for some reason. So again, we want to do a left hand and a right hand estimate. So let's start with the left hand estimate. Okay, so our first estimate, we're considering what happens between 0 and 1 seconds, and we're going to pick the rate on the left for each one. So we're going to do 0 times 1, rate times time, plus, now from time equals 1 to time equals 2, if we pick the rate on the left, we get 3 times 1, plus, from time 2 to time 3, I pick the rate on the left, 5 times 1, plus, 6 times 1, plus 7 times 1, plus 8 times 1, plus 10 times 1, plus 12 times 1, plus 15 times 1, plus 18 times 1. Now, You may be wondering how I was able to go so quickly, but I want to remind you that if we're always picking the rate on the left, that we're going to use every single rate except for 22. So I was just going down the list and writing down the rate and multiplying each rate by my delta t. And I knew that I could use all of them except for 22 because 22 is the rightmost point. So again, I need to add up all of these numbers to get my left-hand estimate. When I add up all these numbers, I'm going to get 84. And remember, my units are going to be in feet because each of these was the rate of feet per second times seconds. So my left-hand estimate was 84 feet. If I do the same thing now for the right-hand estimate, for each 1 second interval, I'm going to pick the rate on the right. So I'm going to use every single rate except for 0 because that's the leftmost rate. So I have 3 times 1 plus 5 times 1 plus 6 times 1 plus 7 times 1 plus 8 times 1 plus 10 times 1 plus 12 times 1 plus 15 times 1 plus 18 times 1 plus 22 times 1. So if I add these all up, don't forget my times 1 here at that 18. If I add those all up, I'm going to get 106 feet. So I want to remind you that in the previous problem, when delta t equaled 2, n equaled 5, our bounds were 74 to 118. Now our bounds are 84 to 106. Those are improved bounds because the lower estimate has come up from 74 to 84 and the overestimate has come down from 118 to 106. So I have more accurate information than what I had before. And again, now if I was going to do my best estimate, I'm going to do 84 plus 106 divided by 2, and that's going to give me 95 feet. So last time my estimate was 96 feet. This time it's 95 feet, still relatively close. So this is a better estimate. Let's look at the picture to see how it's changed. So again, we're graphing our rate versus our time, only now we're doing it every 1 second instead of every 2 seconds. And again, I can get a general idea of what the function is doing by connecting these left and right hand points. What you should notice here is that there's less of an overestimate than before. Because the rectangles are smaller, there's less area that's causing us an error. So again, the left-hand estimates are in orange and the right-hand estimates are in blue. So the overestimate has come down a little bit and the underestimate has come up a little bit. But what did we change, right? What did we actually change within the problem? Because we still looked from 0 to 10. So what changed was our delta t and our n, okay? So our delta t got smaller. So our time interval that we were measuring got smaller, which meant that n got bigger. So if you can make delta t smaller, or if you can make n, the number of rectangles you're using, more of them, your estimate's going to get better, right? So the idea is that, let's say we could measure every half a second or every quarter of a second. Eventually these rectangles get small enough that they're essentially a line that hits the function and the error is gone. The overestimate will come down. The underestimate will come up. And that is our goal here, because the more accurate we can make our estimates, the better off we are in finding our area under the curve. So far we've been using tables, but let's take a step back and do a couple of examples and see how we apply this using our n, our delta t, and our estimate techniques. Example 4. The figure below shows the velocity of an object over 31 minutes. So remember, velocity is a rate and 31 minutes is a time. Part A. Estimate the total distance traveled using a left-hand sum with n equals 2, and part B will be to do the same, but a right-hand sum. So that means we want to use 2 rectangles to estimate the area under this curve. Now remember, the more rectangles you can use, the better your approximation is going to be. N equals 2 is not going to be a very good approximation, but we'll do it nonetheless. So remember, if we want to find out n or delta t, and we have the other one, we can use that b minus a divided by n equals delta t. I chose to use this form because I don't have delta t yet. If I had delta t and not n, then I would have used b minus a over delta t. So here, my b minus a is the length of my interval. So that's 31. My n is 2, which means my delta t is 15.5. So that means I'm counting by 15.5s, right? That's a little weird. So that means I'm starting at 0, and then 15.5, and then 31, right? So that's how I'm counting. And if I want to use n equals 2, that's how I have to split it up. So if I'm doing a left-hand sum, that means that the left-hand point of each rectangle is what is going to touch my function. So that means for my first interval, which is 0 to 15.1, I'm using the 0, which is the lefter of the 2 points, to figure out how high to go on my rectangle. Okay, so my rectangle is going to look like that. And then for the interval 15.5 to 31, I'm going to use the 15.5, which is the left of my 2 points, to get the height of my rectangle there. So my estimate is going to be the area of these two rectangles added together for my left-hand estimate. And again, if you look at the picture, you'll see it's the left-hand corner of my rectangles that's touching the function, because I picked the value on the left of my two possibilities to get my rate, right, which is the height. So if I look at my first rectangle, I know that the width is 15.5 because that's my delta t, and then my height appears to be 20. So I have to do 15.5 times 20, which is going to give me 310. So the area of this first rectangle is 310. Now for my second rectangle, my height is going to be based on the value I get when my independent value, which we'll call t here, was 15.5. So if I approximate the height here, I'm going to go back over here to the y-axis, I'm going to say that that's roughly 15. So 15 units high and 15.5 units wide. I multiply those together and I get 232.5 for my second rectangle. Adding those two numbers together is going to give me 542.5. So that's my estimate for part A, 542.5. And looking at these rectangles, I can tell that this is an overestimate for the area under the curve because there's extra area there. Let's see what happens when we use the same method to look for a right-hand sum. So now, when I'm looking for a right-hand estimate, that means that I'm going to use the height based on my right point between the 2 points to figure out the areas of my rectangles. So again, my first interval is 0 to 15.5. So that means I'm going to pick the height at 15.5 to draw in my rectangle, right? Because again, I need the right-hand corner to touch my function. Now, when I do this for my next interval, 15.5 to 31, that means I'm picking the height at 31, which is unfortunate because that height is 0, right? Which means that the area of my second rectangle is 0 because it has no height, which means it has no area. So that means I just need to get the area of my first rectangle here. So again, I'm going to do width times height. We said the width was 15.5. We approximated the height to be right around 15. And we said that 15 times 15.5 was 232.5. So for part B, I get an estimate of 232.5 plus 0, which was 0. And you can see here by the rectangles that this was an underestimate. There's huge chunks of area missing if I'm looking for the exact area under the curve. So again, we can see that these estimates are terrible, right? They are way off. The overestimate was way too high. The underestimate was way too low. And that's because n was really small. The bigger we can make n, the better our estimate will be. But now if we have a function and we have an n, we know how to draw in our rectangles so that we can estimate areas. Let's look at another example. Example 5. If t is in hours of a 20-hour period, the rate at which bacteria population growing is given by f of t equals 3 plus 0.1 t squared. Find an over and under estimate of the total change in bacteria over this period if delta t equals 4. So we want to approximate the area under this curve. This curve is the rate at which the bacteria population is growing. So if we were to find the area under the curve by estimating using rectangles like we have been, that should tell us the total change in bacteria. Again, it's not going to tell us how many bacteria we have, but it'll tell us how much it's changed by. Now, if delta t equals 4, what do we know about n? So a 20-hour period, that tells me that b minus a is 20, because that's the length of my interval. So I have b minus a over delta t is going to give me n. So if I have a 20-hour period and I divide by 4, that means I'm going to be doing 5 estimates. N equals 5. Delta t is important because that tells me how I'm going to get from time equals 0 to time equals 20, right? Because it's a 20-hour period. So delta t equals 4 means that I'm getting there by counting by 4s. So what we need to do now is we need to set up a table so that we can find the left and the right hand estimates. And since delta t is 4, we're counting by 4s. So 0, 4, 8, 12, 16, 20. It's a 20-hour period, so we stop there. So remember, we put our independent variable on top and our rate in the bottom, right? Which means we need to take each of these numbers and plug them into f of t. So plugging each number in, we get 3, 4.6, 9.4, 12.4, 28.6, and 43. Now that we have our table, we can find a left-hand estimate and a right-hand estimate and use that to find our over and under estimate. So the left-hand estimate, remember we're going to use every single rate except for the rightmost. So we're not going to use 43. So I'm going to do a little algebra trick here. And since I know that every single rate will be multiplied by 4, because these are 4 units each, I'm going to pull the 4 out front. So 4 times 3 plus 4.6 plus 9.4 plus 12.4 plus 28.6. If you're more comfortable multiplying each one by 4 individually, that's fine. It means the same thing. So when you crunch this number, you get 232 bacteria. When we do a right-hand estimate, we don't use the leftmost point. So again, I'm going to pull the 4 out front, my delta t, and I'm going to have 4.6 plus 9.4 plus 12.4 plus 28.6 plus 43. So all the rates except for my leftmost rate. I multiply those together and I get 392. So now again, I need to look at my two numbers and the bigger one is my overestimate. So 392 is going to be my overestimate and 232 is going to be my underestimate. If for some reason this question had asked for best estimate, we would have averaged those two numbers together and we would have gotten 312. So we can see that the change in bacteria is positive, but we don't know exactly how many bacteria there are because we don't know how many we started with. But we have a general sense of how much it's changed over this 20-hour period. So the difference in this problem, again, was that we had to set up our own table instead of having one provided to us. And we were able to do that by figuring out our values for t using the delta t and your interval, b minus a, and plugging them into the given rate to get the corresponding rate values.